Hey everybody, you should be able to hear me now. I'm gonna mute everyone in the room. My little MacBook Air is, what's up, Ben? So if you have your camera on, you might be seeing the video. So you can always turn off your cameras. I might turn off cameras just in case. So we're just gonna turn off cameras. Stop videos on this. Like everyone, I think a lot of people have their cameras on, they've just got them covered. It's so funny to me. So it's pretty good. Yeah, definitely get those camera covers. It's so crazy. I'm just stopping video on a bunch of people's things. Okay, so how's everyone doing? I got everyone muted, so you got to hop there in the chat and you got to say hey to me. How's everyone doing? We got 24 people in. What's up, Maddie? Hey, Maddie. I think saw Maddie this morning. Yeah, Cooper. And so it was good seeing you guys. Substitute taught this morning. So saw Ben. I know I am tired too. That is definitely Sarush. Sarush. I'm gonna turn off your cam there, Sarush. So we are okay. Let's see this. Hey, what's up, Madeline Wilson? Okay, let's get started. I'm gonna drink a whole bottle of Coca-Cola while we're having this review right here. If you guys know, so for those who I substitute taught this morning, it was 8 a.m. and now it's almost 8 p.m. and I'll go home after this, so we'll be good. Okay, you guys ready? It is, yeah. Oh, it's fine. Spring break is next week, so we get to relax. We get to just whole week off. That's crazy. You don't. See, this is the nice thing. It's like sometimes with school, it's a lot of work, and then you just get time off. You get to be like, I get to relax, not do anything. So enjoy. Where are you guys going on spring break as we get started up here? Wait just a minute or two more to start up. I got some text from Dr. Petrie, and he was kind of giving me some advice on what to talk to you guys about. So if you guys want the Dr. Petrie advice, because he's writing the test, we can give the doc. Going home, where is home? Oh, Ben, I know where your home is. Ben, you're from Nashville, I think, right? Am I wrong? Am I wrong that, Ben? Yes. So I hope you get to see your girlfriend, Ben, all that good stuff. So got some library people tonight. You are from Nashville. That's awesome. So let's see here. I'm going to start screen sharing. So sorry, guys, if I get a tiny bit loopy. It's been a long day. Let me pin my video here as the main pinned video. My video. Okay, cool. Okay, so yes. I was just doing 320 talk. So let's hop in here. Let's start talking a little bit now. Yeah, let's hide the chat. Chat. Maybe I'll try the breakout room. Never tried those before. Okay. So with all of this right here, let's take a look at what we should know. And Dr. Petrie sent some great advice. So I'm going to start reading through these texts right here. He said, tips for your review tonight. He said, number one, be really comfortable interpreting MD pattern. Even more questions about that than last year. Oh, would you guys like to do a little MD pattern output interpretation? We can if you want. He's saying it will be on the test. So I'm like, I don't know, maybe we should do that. So we did it this morning a little bit. Maybe we might cover it for tonight, but you guys want to? I don't know. You guys gotta talk to me. You guys know how it is. Should we do MD pattern tonight? People are saying yes. Let's do it. This review is run by you guys. It's not run by me. You gotta watch out. If I fall asleep, the review's over. Just like tune in and I'm just passed out. That's not gonna be good. So don't skim over problem description buildup. So Petrie, and this is a problem I have. He says, do not skim over problems, descriptions, and buildup. There's quite a few questions that assume you've sunk in the time to think about the context of the problem being asked. This is very important for the clustering and validation. So when you think about data validation, let's just kind of do a talk about this right now here, and I'm going to open up a new thing. I think we have some craziness in here. So let's, maybe I'll even do a little aggregate. So let's go ahead and, because aggregate's kind of cool. Let's go here to data. Let's go to survey. Why not survey 9? I'll post this afterwards in the Brian file part of the class. And so let's try aggregate. So what does aggregate do? It uses a function over the different levels of the x's and, excuse me, the y. Brain's jumping out of my head for a second. So I'm going to use all the y's I want, and I guess we could look at gender. Let's just kind of look at some data here for a second. And then we don't need to use aggregate. It's probably not the best way to do it. I wanted to use aggregate, and actually I don't even think that's in survey 10. It's in survey 9 like this. Loopy. So let's move them. Let's just see some things right here. Fun equals. There we go. So we get a little bit of the output right here. It looks a little crazy on the screen, but if you just kind of think about these means right here, it's not the way I would do it. Let's ignore. It's not. Okay, let's do a summary. This is what you should actually do. So let's talk about data validation here real quick, and let's look at this. So when you talk about data validation, this is data collected from Stat Tool 1 students. So when we look through here at the summary, we see that the shortest Stat Tool 1 student is 52 inches, the tallest Stat Tool 1 student is 78 inches. Does that look to be in line? Does that look to be reasonable? So 52 inches would be what? We'll hop here to Petri tip somewhere in a moment. But I should think about what my data is. I should look at this data and be like, what's going on here? I do see something that automatically jumps out to me that data validation here has a problem. Not in this. So what is 52 inches in terms of height? No one knows? 48 inches is 4 feet tall. What's 52 inches? 4'4", you guys are right. 4'4" is what 52 inches is. It's perfectly reasonable that an adult could be 4'4". That's within the realm of reason. We might have problems removing that. But I see something here in this output. I'm going to minimize some of it to make it very, I see something in this that just jumps out to me very quickly that, that is not, especially with people in college. One of the questions you have to know how we ask it on the survey. The question is, what was your high school GPA? And there should be something that just like, and I think it goes to how people misinterpret the question. Is they think it's like, what is your college GPA? And then we've always thought that it's answered this way for a certain reason. And what jumps out to you for the data validation here? Because if you ask someone in college, what was your high school GPA? It should jump out to you. The big thing is, it's the 0, the mins are 0. So that's a huge problem right here. What I would do is I'd immediately take this variable. If you want to do data validation, you're immediately going to take this variable, you're going to toss it in here, and you're going to look at the histogram. So let me make sure this is not blocking anything. But you're going to take a look at this histogram here, and you could also do which, so we can find out these individuals, and we can find out those are the people right there. So as everyone see, I just found them, and then I'm going to go here to survey 10. I'm going to go inside of here, and I'm going to get their rows. So here's all the information. We just stalked them. You can see if something else looked weird in them. If you notice these numbers here, 27, 196, 216, all this other stuff. If you notice, they all have GPAs of 0, as you're noticing here in the output. But this was the code I wrote to find them. I just asked which, individuals, the which, this is a vector of trues and falses, the which gives you the numbers. And important things like that, like Petri does love asking what code output is. So the better you code, the better you understand the code. The better you are with being like, oh, this is going to return a logical vectors of trues and falses. So that returns a logical vector of trues and falses. And then which returns the whats of the trues, which returns the positions of the trues. Then, since these are the positions of the trues, I know it's the row numbers, and I put it in the row space. That's the row, and that's the column. So I just put inside of here the rows I want, and it gives it to me. And I've apparently made a mistake in my code now. It was fine before. So this is what it did right here. Would have been, unless they never, yeah, exactly. Thank you, Ben, right there. 50 points. Let's throw some points tonight. So right there, people shouldn't have this 0. That's a data validation problem. Let's see if we see anything else. Whoa. Weekly hours video game. Can you play 45 hours a week of video games? Sad but true. Can you move 5,000 miles to school? What is the farthest away you could? What is the circumference of the globe? Sess. What is the circumference of the globe?
Here's what I found on the web for what is the circumference of the globe.
She doesn't know that apparently. So you can only really move half the circumference. It seems it's a lot. I don't know about that 5,000 miles. I'm really wondering about that. Can anyone Wikipedia that for me? What is the circumference of the globe? Well, I guess you can move 5,000 miles. You can move almost 12,000 miles. Sarush, another 50 points for Sarush. You move from Japan, wherever. That's a lot. So nice job. I like it, guys. And number of phone contacts. I'm surprised there's only 1,000. Would have thought more. Body piercings 10. I'm not seeing anything else really jumps out to me. Minutes per day on Facebook. This person's on Facebook 10 hours a day. This is the one that really jumps out to me. But what am I highlighting here? You have to actually think about each one of these things. You have to think about it and be like, does that make sense? And this is what Petrie has basically said to me in the text, is that when you're encountering data validation, you have to go through each one and be like, what does this mean? If you notice some of the examples we had in the slides, which I used this morning, was people saying things they have like a car, a 2020, or I shouldn't say that nowadays, a 2021 model car. A 2021 model car. Their model of their car is year 2021. What's wrong with that? You guys should know what you should be saying in the chat. Because if you saw 2021 for the model, I swear, do we not have that survey in here? I'm going to pull this up while we talk about it. Pull library. And the answer is, you can't have a 2020 model car because such a thing does not exist, and they aren't time travelers. I agree. So you can't have those models yet. I don't know if 2020 is out yet. I don't know when they release model cars. I'm not that into it. Let me see, because we did ask a question one time, like, how many days a week do you drink? And I swore it was in one of these surveys. We said, how many days a week do you drink? And people said, like, 10 days a week. So number of drinks per week. There it is right here. Cool. And I guess we could just go straight to it rather than do everything. There you go. This is number of drinks per week. It's what I always think about with data validation. Someone drinks 56. Oh, that's number of drinks a week. It's not number of days. I guess that's possible. 56 drinks a week? That's 8 drinks a day. I don't know. If you look at number of Harry Potter, obviously they were drinking. Yes, I quite agree. We could go through here and we could look at all of this a lot more, but I think I've kind of covered the numbers hours you've been awake. This person right here has been awake for 5 days. Possible, I guess. Seems possible, maybe. I think it's the most extreme. This person has 20 speeding tickets. Weeks in longest relationships. I got them beat, maybe. Number of significant others. Oh, see, this makes me miss the questions we've asked. Oh, this person had their first kiss at 0? That doesn't count. Your mom kissed you on the head when you were a little baby. This doesn't count. That's not a real kiss there. So you can look and you can see issues, especially with the way people answered questions. The whole thing is you have to immerse yourself in this data, and you have to think about how each question was asked. So, just looking through here, I can think, what this person has an average shower length of an hour. I don't know about these things. So it's most miles run one day. Ultra marathoner could do that. So you got to watch out. You have to think about how each of these are done. You know what I find interesting about this? This is on average, how many times a day do you brush your teeth? And we asked this to 628 students. What do you find interesting about this variable right here? And then we're going to hop topics, and I'm going to see what else Peter said. What do you find interesting about that? We'll do MD pattern next. I find it interesting no one said 0. I mean, I know there's people not brushing their teeth. So I'm not saying that personally, but out of 628 students, someone's not doing dental hygiene. We can't really correct for that, but that seems one of those response bias questions going back to 201. Yes, everybody, apparently everyone's dentist loves them. Yeah, I know. Even though it's an anonymous survey, people don't want to put down 0, which is the crazy thing about anonymous surveys. People are like, I brush my teeth. Brush those teeth. Let's look at some MD pattern right here. This was the mice package, and I'm going to show the thing that I love. Blame social norms. Damn social norms, telling us how to be a good person. So I think it's survey. Well, this is gonna be too long. Let me put some brevity in here. Ooh, that's crazy. As I said, it's gonna be too long. We want all the rows. We want columns. Okay, so columns 1 through 5. So we're gonna see something interesting right here. We get the little nice kitty cat, which we so rarely get. I showed this morning, but it's funny when I was making the test last year for my students. It's funny that you don't even realize what this thing is because you rarely get it, at least with class problems. This looks a little bit crazy. I'll do an easier example to read and to see here in a moment. And I think maybe if I walk you through what's going on, you'll be able to I see it. So let's do this. Let's go to survey 10. But what this means, I'll tell you what this output means. Please slow me down or ask questions. That'll help me know where you guys don't understand a topic. What the MD pattern does, MD pattern looks for patterns of missingness. MD pattern looks for patterns of missingness. Does that make sense? What you see right here with this 579 is there are 579 rows in this data set. And if you look here at survey 9, there's 579 rows, and I use survey 9, where nothing is missing. As in, from these 5 variables I'm looking at, 0 of them are missing. And they're missing 0 times and 0. This is like the least interesting one to look at. So what I'm gonna do is I'm gonna run this same thing, but with survey 10, where the variables are a little easier to look at. What I'm gonna do is I'm gonna start punching some holes in there. So I'm gonna go into survey 10, and let's do some removal of data. So survey 10, I'm gonna go to row 1, and I'm gonna go to column 1, and I'm gonna insert a missingness. Now this is going to remove someone's gender. Now watch as I change the pattern. Do you now see somebody's gender has been just deleted right there? So with this in mind, we put an NA in for that. Let's go to a different individual, and we're gonna go to the second individual, and we are going to remove, I don't know what the second thing is now, because it's not quite in order anymore, but we're removing another characteristic. Do you see how every time I'm changing this, do you just watch as I'm changing this output to where I deleted that person's height, I just removed it. And if you notice here, height is now removed for an individual. Does that make sense? Now I want you to think what MD pattern will occur when I do this. Like, I want you to just think logically what's gonna happen here when I do this code right here. What MD pattern will I get at the very bottom? You'll see something at the bottom now, and what will it look like? And if you understand what I'm doing, you will understand what's going on. What will I see at the bottom now? Think, I removed height, and who did I remove it for? If you know what the pattern will look like before I run it, probably understand MD pattern. It was the same person as the first. And since it's the same person, it's actually gonna change this output. Interestingly, I think we'll still have 3 rows, but now the bottom row has changed. Because now one person, think about this. Just remember how you said one person, right? One person has NA for gender and for height. So one person has NA for gender and height, and you can see it right here in the code I've created where I moved gender from that one person, and I removed height because it's the second column in the data frame. They're the first individual, hint by the row, and they're the first individual here, and we removed their first column variable, and we removed the second column information on them too. And that's them right here. We could go to the third individual, and we can move gender for the third individual. And you'll see that's back. I can't even speak today. So now we have one individual who's missing their height data. one individual who's missing their gender data, and one individual who's missing their height and gender data. And just take a look. I'm going to organize this a little bit better than you could see. So do you see right here, individual missing both? This is the individual. And this is the individual. So these are the individuals right here. Now I want you to tell me how many total missing values are there? And hence, I've been making this to show it as we do it. How many missing values are there? There are a total of, you can see it on the screen right there. There's a total of 4 missing values. You can see what I entered in. Let's do something crazy here. Let's go here to survey 10. Let's try something. Let's try some interesting code. Let's go from the 4th through 10th individuals and go to their 3rd characteristic. Let's put in here NAs, and to heck, let's just hit these people right here. Cool. And now you see MD pattern has totally changed. So I've made it a lot more complicated by adding it in right here. There are 7 individuals who are, and I'll make this a little bit bigger here. We'll zoom in. It's probably gonna be best if we. There are 7 individuals. Of course, desired weight's going way off the screen. There are 7 individuals who are just missing their weight. There is 1 individual who's missing their height and weight. There is 1 individual who's missing their gender and weight. There's 1 individual who's missing their value for their gender and their height. There are 2 times in this data frame we are missing gender. You can see that, that's from previous. There's 2 times in this data set we're missing height. And there's a total of 9 times we're missing weight. And if you look here, this vector of 2 through 10 is 9 numbers. I can go right here and show that by going down here and doing length of the vector, and that is a vector of length 9. So it's confirming once again that I removed it for 9 individuals. So this right here is the total. You look right here at this 9, that is the total amount of times that weight is missing. Where this 13 right here is the total amount of times everything is missing. If you think how that is found, it's 2 plus 2 plus 9 is 13. So that's everything we have right here. These numbers indicate how many red spots there are, which we can see, and I'll go do it with survey 11, or one of these. I think it's this one. Maybe it's survey 10. Get ready for some craziness right now. That's not as crazy. Okay, wait. 3, 2, 1, get ready for some craziness. Uh-oh, not crazy. It's survey 09. There we go. So this would be way too much to look at, but it can give you some idea what's going on. If you notice here that there's a 5 right here, that means there are 2 individuals who are missing 5 variables. And you could actually figure out what those 5 variables are by just looking at this output and seeing what the last 5 variables are that it reports. So we're missing the value for X18, that's one of those right there, but it's the last 5 variables it reports, so I can just skim the output if I really wanted to. But this gives me an idea of the pattern of missingness. It seems to be centralized around 5 variables. We'd never put something like this on the test, but you should be able to kind of see that this number 5 represents that there are 5 values missing for 2 individuals. Does that make sense with this crazy output right here? So this right here, there are 4 values missing for, I cannot see, maybe 4 individuals, I can't see, it's very hard to see. But those would not be fair MD patterns to give you on a test. Something fair to give on the test, like this is probably too fair, but you know, we might make it a little bit longer. You know, we'd make sure the variable names look nice and neat on it, but things like this are kind of, you know, how we'd expect you to look at it. Does that make more sense with the MD pattern? Does everyone understand what's going on? That examines where the NAs are. That's the main thing it's doing, is it's examining where the NAs are. So that's that. So quiet. What questions are there? What are people trying to understand? I'm not used to silence. Can we talk about lift? Yeah, we can talk about lift. Let's talk about some lift. Let's talk about that lift. Everything about clustering. Oh, Petrie, and we'll remind me if I don't get to it. We'll end at about, what is it? It was 7 when we started. We'll end about 8:30 or so. Brian, is the sheet of notes front and back? It is front and back. Great question, John. Front back notes. So Petrie said front back notes, and we'll probably look at Petrie's slides here on how to take the exam in a little bit. I pulled those up too. But let's talk about lift a little bit here, and I can maybe throw in some tips for your assignment. My brain's woo, going nuts. Let's go ahead here, and I'm going to pull up some of the notes. And we're going to talk about lift and how to interpret lift. I'm going to probably throw down some hints for your assignment. So let's do this right here. Let's hop in here, and let's go into associations. Now, I was doing this morning in the morning class to talk about how to interpret. And let's use the R output. Let's do that. Petrie writes all the slides in R, which impresses me. I'm just like, you got skills beyond what I'm capable of. So he writes all of his output inside of R, or all of his notes. And so let's go down here. Did I grab the right one? I feel like I've done something crazy here. If you're talking about the choose right here, I'll mention briefly for those who have questions. I've had a lot of people ask me, Brian, what's going on with this choose thing? And thank you, John, you are right there. Handwritten notes, front back, handwritten notes. So thank you for answering all that. So what this is, let's talk about what choose does for a moment. The choose function is if you have 5 people and you want to look at how many ways you could choose 5 people with 5 people, what would be the answer? If you have 5 people in a room and you're looking at how many ways you can choose 5 of them, how many ways would there be? If you have 5 people and you're choosing 5 people, the answer is 1. If you have 5 people and you're picking one of them, 5 people pick 1, how many ways can you pick 1 person from 5? 5. So this right here is saying, and if you had 120 artists and you wanted to make a rules of length 4, that's how many ways you could do it. And it kind of gets to the whole a priori learning method, that if you have a whole bunch of ways that you can make rules, well, just with 120 artists making rules of length 4, which mean, 3 are in the antecedent and 1 is in the consequentant, then antecedent is the start of the rule, left-hand side, and consequent is the right-hand side. So if we looked at the ways we could make the rules, then there'd be a ton of ways. So that's why we use the a priori learning method to kind of limit what we're doing. We try to limit as much as we're doing. And I should have everything in here, like grocery stores. Yes, I got that grocery store transaction in here. At least it looks like I do. So I got a lot of data on this computer running in the background. This little thing's humming away. If it starts to hover off the ground, just tell me. Curious, it takes off. Okay, let's see what we got going on here. We got some item frequency of the top items. If you don't do top, it won't order it. It's kind of an interesting thing about this function. If you don't do top, you don't get the ordered and it looks all crazy. It's kind of nice. It makes a Pareto, so it's all crazy. But if you put the top, I think one of the quiz questions was what is the 10th most common item? So you can just put top 10. It's sausage. Didn't know that. So shopping bags. Maybe this is Trader Joe's. So you can do that right there. Pretty neat function right there to do the item frequency plot. I really like that one, especially top puts it into a Pareto, which is an ordered bar chart. Good stuff right there. Let's take a look. We got some item frequencies, and let's take a look at some rules right here. Oh, gotta love the rules. Okay, so we already got the rules. Inspect our rules. Well, what do we got? So let's make sure we can interpret this. And wow, I love these rules right here. So with these rules right here, and if you notice, we use the a priori learning method. Let's just talk about briefly what the a priori learning method does again. I'm gonna move this to the side. So the a priori learning method right here is the following. We can control how we look at rules because there are a ridiculous amount of rules to look through. And rather than look through endless rules, we can say, I only want the rule to have a support of 0.001. So you could do something insane here and put this to a support of 90%. And now probably, are we even gonna get anything? It looks like it doesn't like it. The rules don't exist because there was nothing that met that condition. So it did not like that. Bad idea. As long as I didn't break it, everything's good. So what that actually did is there was no rules to look at. Nothing met these criteria of having a support of 0.9 or whatever it was I entered in. Nothing had a support that high, a confidence that high, a minimum length of 2, and a maximum length of 4. Probably we'd get the same output if we delete min length, just as another argument you can do there. But you don't need mid length, and there they are right there. As far as seems to me, that's the same output. The length controls the length of the rule. So if you wanted to only look at, hint, hint, rules with 4 things in the antecedent, that is the start right here. So if you wanted 4 things in there, and of course you need a right-hand side, what would be your maximum length of a rule? If you want to look at rules with 4 things on the left, your maximum length would be what? Let me change that. Maybe we'll make max length 2. You'd want 5, and I don't know if people are saying that as the new answer on here. Let's change, because we're looking at the notes output right now, so let's change this. Let's go length 2 right here and take a look. Oh, it doesn't like that? Oh, let's drop that confidence. Let's see if it likes it. Are we out of bounds still? Oh, we got it. Cool. Okay. If you notice the confidence was too high, we might, and look at this, we're only going to get 1. Well, it's going to say script out of bounds if I run this, but what I can do is I can just go down to my rules here now, and you see we only get that. If you notice, I start to move this back a little bit, and now I get those, and now it's to the point where I really need to limit my rules. So let's start reading off these rules and interpreting them here. And is rules one-dimensional? Rules is one-dimensional. So it prints it out for you like that. That always confuses me. I get a script out of bounds on that so much because I'm thinking it's 2-dimensional when I work with it. But the rules is just like a list of rules right here. So you just put it in spec and tell it the number of rules you want. Okay, so let's look at this honey and whole milk. So what's going on here with this honey and whole milk? Well, you should be able to interpret everything in this output. So interpret for me what this count is. From the count, I can figure out how many transactions there are on the data set. My math brain's like slowing down today. But the count would be the number of carts that what? The count would be the number of carts that what? Yes, the count is the number of times that people have honey and whole milk together in the carts. Yes, and we should be able to, let me try to write some code here on the fly. Let's see how well Brian's brain is turned on right now. So let's go to subset. Let's go to, we got the transactions here, right? So let's go to the is it under transactions? Cool. Subset, transactions. Okay, let me see here. No, I don't want to subset those rules. Transactions. Transactions. Let me just try a few there. Percent in percent. Actually, percent AI in percent. Let's try this. I'm going to fail miserably. Watch this. Hopefully not. And let's wrap this in a which. Oh no! What is going on here, boys and girls? What is going on? Was it called transaction data? Oh, it's called G. Not lowercase g. There we go. Okay. I was like, what is my data called? Usually it's called transaction or something. And then let's just go here and wrap this inside of a length. Guess what the answer is? The answer is 11. There we go. I don't know the name of my data frames or my rules or all that stuff. So there we go. I got some code out of the way. But I want you to notice why I'm using percent AI in percent. This is a big thing, especially with the homework assignment here. Percent AI in percent means it has both. I call that the all in, where the difference with percent I in is that the carts have either of those. So carts that have, and maybe we'll do some calculations here in a moment. Carts that have either honey, whole milk, or both is 2,517. Carts that have both honey and whole milk are 11. So what we could do here is we could take the carts that have whole milk. So what percent of carts have whole milk? this is now the support, or the total of carts that have whole milk. So this is the amount of carts that have whole milk. And now this is the amount of carts that have whole milk and honey. I'm gonna take a guess at what this is. I want to say this is about, I'm gonna say this is, well, no, wait. This is given a cart has, oh, I need to reverse it. Given a cart has honey. If a cart has honey, what's the probability it has whole milk? So given a cart has honey, what's the probability it has whole milk? And the answer is, look at this. Does everyone see that? 0.77. So given a cart has honey, and do you see what I just read? Given a cart has honey, for all the carts that have honey, what is the probability it has whole milk? So these are the carts that have honey and whole milk. So we kind of said, of all the carts that have honey, what percent of them have honey and whole milk? So when you read this rule as follows right here, and this is helpful for the homework too, given a cart has honey, what is the probability the cart has whole milk? Like, a lot of this reflects around that. Like, how does it impact it? What's the probability? And the support is as follows. 0.0011, yada, 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 percent of carts have honey and whole milk. So how many transactions were there in this data set? Let's look at the G. Where's my G at? G should be up here somewhere. Formal transactions. I'm going to tell me the length of it. I can get length of it, right? So if we look at length of G, please ask those questions. I know I've been talking a while here. There's 9,835 transactions. So if I figure out this right here, this will be this 0.0011 right there. If you notice, just so you can see this number right here. Oh yeah, I just hit the wrong button. This is the exact same number right there. And does everyone understand how I'm getting these numbers and how I can kind of talk about them? And I have right here the percent of carts that have honey and whole milk is the support. And I found it out by saying, out of how many total transactions are there carts that have honey and whole milk in them? And that is the support for the rule as defined by right here. This is the percent of carts that have both honey and whole milk, where the confidence is what is the new probability of a cart having whole milk given it has honey. This is the posterior probability, the new probability. What is the original probability of whole milk? What is the original probability of whole milk, and how do you find that? I haven't seen the test, but I swear I think teacher's gonna ask this one. Like, what is the original probability of whole milk? I'm gonna find it the hard way while you guys find it the easy way. Find it the easy way for me. What is the original probability of whole milk? It's not too hard with the code right here. Okay, I'm ready for the answer. Find it out. I'm gonna make you guys answer this. What is the original probability of whole milk? It's easy if you do it the easy way. We should get the same answer here. What would you do to find the original probability of whole milk? Think, this is the probability that, since you know they have honey. If you know they have honey, the probability of them having whole milk is now this. Given a cart has honey, the probability of whole milk is the following. To find the original probability of whole milk, we do what I call, nice job, careful, Michael, you are right. It is confidence divided by lift. So let's take that confidence right here and divide it by the lift. And we're just going to do what I call unlifting it. If you unlift the confidence, you get, and be careful, it's confidence divided by lift. Because confidence is the new probability, so we're going to turn it back to the old probability by unlifting it. And so you can say that unlifting the confidence is going to be our original support of whole milk. You can say support of one item, and that would just be the item frequency, so I could have just ran item frequency, but why do it the easy way? So we get the answer there, and we get the answer there, same answer. And that's what we want to do, is we want to be able to, think about it a few different ways, because all we're asking is, originally we're like, well, what is the support of whole milk, as in what percent of carts have whole milk? Well, remember, we have here that the probability of whole milk given honey is this, which has been increased by a factor. So we can do the two interpretations, and for the assignment, we can do the two interpretations where the probability of whole milk has been increased by a factor of 2.870009 with the information that honey is in the cart, or a cart with honey is 2.87 times more likely than a cart by random chance in the store to have whole milk. So when you talk about it by random chance, which is also a mathematical calculation we can do, these carts are 2.87 times more likely than by random chance to have whole milk. Am I correct? How does honey impact whole milk? Correct. So did that help you guys with those interpretations right here? All the other ones are going to be the same, just with different wording, like giving someone has meat spreads, they're more likely to have yogurt. I guess are meat spreads like maybe like you know, like lunch meats? I mean, like I buy lunch meats and I buy yogurt, so you know, maybe there's something to buy in lunch meat and yogurt, but I do not know what meat spreads are. Is that like spam? I don't know. What are you guys thinking? What are your questions on kind of this lift support? I do want to say this. If we're doing this with missingness, then when you do it with missingness, you have to remember that it's given the left-hand side is missing, how does that impact the probability of the right-hand side missing? Given the left-hand side is missing, how does that impact the probability of the right-hand side being missing? Keep asking those questions. Brian, review this. Tell me what you're thinking. We've got another 50 minutes. Can you repeat what the lift percentage indicates? Cool. Amount of Coca-Cola. So what the left-hand side indicates, or what the lift indicates. The lift indicates two ways to interpret it. It is the percent increase in the probability of the right-hand side with the information that the left-hand side is there. It's the percent, and it's a, excuse me, I should say factor. That was my brain turning off for a second. It's the factor increase in the probability of the right-hand side given the left-hand side is there. And that's one way to interpret it as a posterior probability. The other way we interpret it in the notes is the lift tells us how much more likely we are to see the right-hand side than due to random chance. So we can talk about the random chance way of saying it, that it tells us how much more likely it is than by random chance. The probability of whole milk by random chance is 2.555. And then if you notice, well, we're like, what is the lift here? I can grab this lift right here and we'll get the confidence, because the new probability with the information we have is that we are 2.87 times more likely to see whole milk given honey is there, which that is 2.87 times more likely than by random chance. Kind of blending both interpretations there. Does that make more sense to you, Connor, right there? I hope. But it's a factor increase. And make sure you know it's a factor increase. Lift can also be less than 1. Yeah, good. There we go. Keep asking those questions. Whatever you guys want to review, I'll talk about, and I'll go through. I really think outputs. Oh, I know something else Petrie said. Let's hop over to the. Exactly, Madeline, you are right. Let's hop over to that k-means clustering, because another thing Petrie said, so I'm reading to you Petrie right here. You'll want to be really good, take notes on this, you'll want to be really good at interpreting cluster centers and coming up with descriptions of what individuals in each cluster look like. So the cluster centers he's talking about there, the k-means algorithm. The k-means algorithm is going to find these centers, and it's going to tell us where the cluster centers are. So we're going to need to interpret that, and we can kind of bring up some data here. So let's go back to our notes. We can talk about some clustering right here. Let's go over to clustering, and let's hop into clustering in nearest neighbors. Let's do it. Okay. This is one of my favorite things we do later on is support vector machine. You said be really good at interpreting cluster centers, and what else? Let me read it again, verbatim. So you'll want to be really good at interpreting cluster centers and coming up with descriptions of what individuals in each cluster look like. And so earlier today, and we might look at that one too, when you think about it, we did the iris data set. So let me hop down here to the iris, so here's the data iris. And so let's see here, we're just running some stuff. I don't know if I need to run everything above. There we go. Okay, maybe, you know what we might do? Let's try something here. Let's grab this. Let's go ahead and take, and so we're gonna take this code, 2 seconds. Has anyone asked about 1B from the homework? If that's on the test, it'd be nice to know. What's 1B say again? I can't remember. If you copy paste part of it in here, I'll probably remember. Is 1B, that's not the choose one. Copy part of the question. I'll see if I can help you out or explain a little bit. I'm gonna run our own stuff right here. We need to scale it, don't we? Ah, darn it. We don't need to know anything out. So let's scale it. Okay. Let me do this. I'm gonna write some code here real quick and hopefully it works. I'll give you just put 1B. 1B. That's the only thing you give me. All right, give me a half second here. I'm gonna write this out, then I'll go look at that in a second. So, oh, Dr. Petrie's here. Hey, that's awesome. That's so cool. So Dr. Petrie can type in the back. Good job, Ryan. Back to making the exam. Thank you, Dr. Petrie. I was like, that person's being really direct with the answer. So let's take a look at some data right here. Okay. So let's go in here and let's go to survey scaled. Okay. Cool. We got a categorical variable in this one at the start. That's what I thought. Gender is the first variable. Let's see what this data looks like. See, don't tell Peter that happened. So let's take a look. I've got glimpse still going on right now. So I'm gonna take a look at this. Let me just glimpse the start of it though. Glimpse one vector or two. Gender, height, weight, desired weight, GPA. Is it mad about that? Oh, I'm doing rows. Don't tell anyone that happened. So there we go. Okay, cool. We got the scaled data frame now. If we just look at this data, it's all z-scores. If you look, everything's been z-scored. Ooh, it's a good question. Why do we center and scale stuff? Why do we center and scale? What's going on with that center and scale right there? Maybe we should take a look at this because let's go ahead and take a look at some of our data that we just centered and scaled. So if you look right here, and I've got my plots messed up a little bit, looks pretty good. We've probably got some issues that some of these are not normal. Yeah, they've been z-scored, but just because you z-score something doesn't make it normal. So we could worry about transformations on this later on. So this might not be the best application of the k-means algorithm because some things might have undue influence. We've got some outliers here that are going to cause some problems, but I am interested to see what goes on. So variables with large ranges don't exactly, Curtis, nice answer. So variables with large ranges or extreme outliers don't dominate, and that's what we don't want them to do that. That's in the notes a lot with the shoe size and the salaries and individuals. So all we're doing is we're just altering the code just a little bit here, just a little bit. And we're just gonna take and change this to survey scaled, and let's just work with the code right here. We got the set seed, get the same results. Oh no, did it totally bonk? Of course things are gonna break. Survey scaled, and let's see right here, what did it say? Do no function in the function argument 1. We might just take a look at the output right here. Let's just drop it down dimensionality wise. We will ignore that. It is not saving. I have failed you. So let's just take a look at the classic stuff we got right here because this is currently running. Oh, is that? Oh, you know what I think it is, guys and gals? Uh-oh. I think I was the proprietor of my own demise. Please, for 100 points, someone tell me what it is because I know the answer. So what happened? Why did everything explode? And why is Brian laughing at himself? The answer is, no, it wasn't that actually. It was all those NAs I entered in. You guys remember earlier when I threw in some NAs? And if we look at the warning code, it's throwing back some NAs that caught my eye at the last moment there. It's not able to run the k-means algorithm due to NAs. So it wasn't able to actually work with the dissimilarity matrix and all that good stuff. So or not the dissimilarity matrix, but it wasn't able to figure out the distances between everybody. So because of the NAs I entered in to talk about MD pattern, I totally destroyed everything. So I was like, why isn't this working? And I didn't want to really debug code. But so the NAs were the problem. Those NAs I entered in way back at the start here when I was tossing in some NAs. That's what did it to us. But we do have some people here And we're gonna restart. We're gonna kind of walk through this algorithmically, and we're gonna look at this right here. I like this. Okay, let's look at these groups right here and see what's going on with these people. So what do you think about these people? Tell me about group 1, tell me about group 2. These are Stat Tool 1 students. Tell me about these people. It basically, it basically did what? You guys got to write me a sentence. Write me a sentence about these people. What do you think about them? You have anything to say about them? Nothing? Surely something. Write me a sentence. I think Peter was answering another question. I'll go back and answer that other question or talk about it in a moment. Everyone is silent. Do you have any ideas about cluster 1 and cluster 2? Surely something. I don't know how to describe them. I don't even know what these are. What are those things right there? What are all those? What are those? Like old memes. Oh yeah, here we go. Tall people are heavier and want to be heavier, and short people are kind of. I mean, slightly over average. And what I would do, if I had to write a full sentence on the test, here's what I'd write. Cluster 1. Oh, wait, Curtis, what do you got, Curtis? Curtis says cluster 2 is pretty average except far below average for GPA. Cluster 2 is below average for GPA. Cluster 2 is slightly below average in all qualities. They're most normal in GPA. Cluster, oh, maybe you're, Are you guys looking at my, let me do this. Let me clear out this. Sorry, you might have been looking at, I want to only look at this, and I'll explain why. Oh yeah, that's why I figured. I was like, wait, sorry, I just jumped a bunch of output to the screen. Cluster 2 is slightly below average in their height, weight, desired weight, and their GPA is, it's the closest one to average, or a little bit above average. And actually, you know what? This makes sense to me. These clusters are really a lot like guys and girls. These are guys and girls right here, because height, slightly above average, weight, slightly above average, want to weigh slightly above average, GPA, a little bit below average, a little bit below average. We're looking at Z-scores right here. And then think generally like little bit below average, a little bit below average, a little bit below average, a little bit above average. So here's what we do. When we see that we can come up with some idea of kind of what's going on right here, what do we do? If we've kind of got, this looks like this looks like this. Like we're like, makes sense. Like those are good clusters. As soon as we're like, that's a good cluster scheme, what do we do next? And it's almost counterintuitive to some people. What do we do if we say we have a good cluster scheme? Another cluster, another one. Just keep doing it. All the memes tonight. Okay, what do we got here now? Oh my gosh, look at this. And it kind of makes sense. I think I know what happened here. We've been playing around with this data all tonight, and I think I know what cluster 3 has in it. I think I know what cluster 3's got. So we could save those cluster IDs. Not the NAs. We knocked off those NAs. Cluster 3 is really low in what? The outliers for what? GPA. Yeah, cluster 3 is really low in those outliers. So, when you look at this right here, we're seeing that people are really low. And we can just steal some code right here, because what we can do, we're just going to take, because this is just taking and appending all this right here. We're just going to steal some code for the moment. So, and let me make sure I go to the right portion of my code. I'm just going right here. Let's go in here. Whoops. Oh, geez. Oh, my other recording finished I literally finished another review for this. So we're just going to go here. Survey with cluster ID, and survey scaled. Sure, why not? We'll append it to that. And survey ID with cluster. I might have the wrong code. Cluster ID right there. And it's 2. We can just probably, it's going to work. We'll find out the hard way. I think I have a mistake in here. That did work. Cool. So survey scaled should have the ID on the end of it. Cool. With this in mind, I'm going to make a table here of survey scaled $ID, and that's what I thought. I just think about what we have here with our clusters is when you look at this right here, just look at the output. Oh wow! And then we've got the did I just rerun the clustering scheme with? I think I just reran the k-means algorithm on that. Oh, is it not using the ID? Oh yeah, because I didn't run it. Okay, hopefully it didn't take it. We'll worry about that later. As long as I got the same output. Looks like I did. No, well, it shifted the number of the groups, which it can do. But with this in mind right here, remember group 3, as long as we'll just pretend if I shift it or not, only has 16 individuals in it. And when you look at these individuals right here, it's people basically, and actually let's do the aggregate function on it. So let's do an aggregate of, let's do it based on ID. And we're gonna do of survey 10 scaled, brain's breaking right there, data equals. I know, it's got in there. So it is supposed to be y tilde, yeah, that's right, y tilde x. I think we got it, and then we didn't do a fun, of course. Fun equals mean. Okay, cool. If you look at right here, these people have a GPA, and these are the z-scores right here. So what we should do is we should append it on, like it's done right here, to the non-scaled data. So let me just do this. We haven't reordered the data. So let's go here, and let's take our original data, and I'm gonna take all the questions. But I'm gonna take these cluster IDs, and I'm gonna put them back to survey 10. Survey 10 does not have ID yet. And then when I aggregate right here, I'm only gonna aggregate survey 10 based on the first comma 2 through 5, because I think that's what we did. ID not found, did I not append it on? ID cluster, is that not appended? Survey 10, it does have ID. Oh my gosh, everybody. I know, no, Curtis, I know. I realized it right at that moment. So I wonder, let me try to do one thing right here. Okay, how many variables does it have? Curtis, you are so correct. Survey 10 has 21. So 2 through 5, and let's append on 21. Got it. Nice job, Curtis. Because I was limiting my data frame, I was like, I thought I put it on there. So if you notice right here, the people in cluster 3 are dramatically different. And if I change this to median right here, we're gonna see here, nice job, you guys are catching my little errors tonight. But if you notice here, we see that cluster 2 is our people that are slightly below average in height. It just, what do you think generally the average height for women is? What is like the general average height for women? Like maybe 5'5"? What do you think the general average height for men is? Maybe 6 feet? What's the general average weight for men? This is just a random example, and it's actually kind of working. So we have basically cluster for people who view themselves as female, cluster for people who view themselves as male, and we have here the cluster of people who don't have GPAs, because when you get that third cluster, it kind of clusters them off, and we're able to reduce the sums of squares with that. So that's the best way. Maybe we'll talk about some elbow plots here in a second. But, and I might go back to Preston's question. I think a few people, not Preston, a few people had the question. I can't remember who had it, but we'll go back and check that out. What we need to do now is we actually need to look at that third cluster right here. Let's go ahead. Where's my code to increase the clusters? Here we go. Let's go to 4 clusters. Let's see what happens. Let's have some fun. So I'm increasing the clusters to see if adding a 4th cluster helps. And let me remove the scaled. Cool. Okay, now we no longer have those cluster centers because that was creating some issues, I think. If you notice, we still have the people here with horrible GPAs, but actually this arises an interesting 4th cluster of the people who are very tall, very heavy, want to be very heavy. And so really, I think there's a fourth cluster here. And so with this in mind, I think I'd go for a fourth cluster. Very interesting right here with what we get. And as long as I have my code lined up properly, let's see here. And there's the four clusters. So we can take a look at our four clusters right here with the means or the medians, whichever we like. Medians are not going to be impacted by the outliers or the skew. And you can see here, these are our people who generally are taller, weigh more, and want to weigh more. And you can see that's really the key characteristics as we were looking at them right there. So kind of being able to describe them, if you look at, I have the Z-scores versus the medians. We always want to bring it back to the original data. But when we work with the data, we want center and scaled data that is not going to have undue influence from those extreme values. And I didn't transform, I didn't scale I didn't make everything nice and perfect normal, but it's an example problem. How are you guys feeling about all this? This has been a lot on the k-means algorithm right here, which we've talked a lot about the mechanics behind it, but kind of interpreting this output. And technically at this point, what I should do, other than defining characteristics within the clusters, could you talk a bit about clustering, defining characteristics between clusters? So sample question, but I'm guessing 0, 0 is the average. That's the median. That's the median right here because I ran the function median on it all. I can find the mean. There's the mean, 0.66 is the mean. But it might be due to some skew. And if I run this aggregate at this point, since I'm using this value right here, I'd probably want to throw it inside of a round. So I would just toss it inside of here and do that. And I'd get 2 decimals is usually fine for a bunch of stuff. So I wouldn't, instead of putting my output that way, I'd just toss it inside of a round. So with this right here, I see some different characteristics among it. Could you talk about cluster defining characteristics between clusters? Well, does Curtis, I'm trying to make sure I do it correctly here, but other than defining characteristics within clusters, let's do that right here. How does, and I'm gonna kind of hop back to the Z-scores on this, because it's a little easier to look at the Z-scores. These people are just flat out average in everything. They're just average Joes or Janes or whoever's. And look at this, boom, GPAs. Like, how do they stand out? Like, they are way different in GPAs than everyone else. Really, when we talk about it right here, things that should jump out to us immediately are Z-scores outside of -2 and 2, because 95% of Z-scores are contained within the interval -2 and 2, or 1.9599 if you do actual Z-scores. But uncommon Z-scores are basically -2 and 2. And we do see weird stuff. It's like, well, these are the people who are very unusual. And you kind of have to look at it as a whole. Like, when you talk about your general above average people, well, here's your pretty above average people. Now, Z-scores that definitely start with a 0 are not unusual. I don't need -0.4. We could run the math on that to figure out exactly what percent is below -0.4. It's not a lot. It's less, it's about 30, 34% maybe, but that's not super uncommon. So the key defining characteristics of these people is they're bigger people who want to be bigger. I mean, when you look right here, it's interesting. It's just interesting that it's like they weigh more, their weight is above average, and they want to weigh more. And how do they stand out from other people? Well, when you think about it, a lot of people, if you say, do you want to be 240 pounds? They might say, no, I don't want to be 240. So frankly, I think if I had to define this cluster, who do you think this cluster, it might be bodybuilders. Yeah, people who work out, like go to the gym, work out. And that's really one of the key defining characteristics, I think, right there. So and the thing is, and I want to mention this is unsupervised learning. There is no right answer, but we should have a kind of, I was thinking like, it's like these people are working out. If you say, I want to weigh 240 and I weigh 230, it's like, well, and they're also taller, but when you look at the difference between, they're a decent bit taller, they're in the top, I guess that's nearly the top 10%. The Z-score for that is 2.1828. So they're about at the top 10th percentile of heights on average. So they're about at the top 10th percentile of heights, but their weight is in the top 1%. The top 1% is 2.3263. I've not said one in a long time. But they're in the top 10% of heights and the top 1% of weights. You don't have to get this specific with Z-scores. It's just I've been doing this a bit. This is the top 2.5% as defined by 95% confidence intervals. So these people are taller people who weigh more and want to weigh more. That's their kind of key characteristics. How do they differentiate? You just kind of create this image in your mind of them, of like you said, a bodybuilder, someone like that. You just kind of think like our people who are taller, bigger, want to weigh more, and all that stuff. We got our slightly above average people in the characteristics here, and our slightly below average people in the characteristics here. And then we have this key defining characteristics, which really jumps people out here on that. So really, there's just the group that they're pretty average in everything, except their GPA is really horrible, or they answered the zeros, which that goes back to data validation. If you notice, all of these things are intertwining. So as we should, let's hop back here. Let's run our code again, and let's bring it up to 5 clusters, because why not? If we got differentiation between 4 clusters, we go for 5, and I'm crossing my fingers I don't have to interpret all 5 clusters, because I got my horrible GPA people. And I want to mention this. When we do the k-means algorithm, does it just like break off from the clusters? Is that how we get all the new clusters that are involved? Is that what happens? The answer is no, it's not how it happens. When we add a new cluster center, everything is kind of redefined among the clusters. Now, you will generally see things stay together to a certain extent, but just because something was in a cluster does not mean it's in the same cluster now. People will kind of shift, or items will kind of move around to whatever one they're closest to, which reduces the within cluster sums of squares the most. That's the whole goal of this. We'll look at some elbow plots maybe here in a moment. But with this in mind right here, we see our bad GPA people. We see our bodybuilder people. So we do get these clusters again of those individuals. We're going to call those the bodybuilders. Then we have here our slightly below average people. And wait, look at this. I'm not liking this. Cluster 2 is my slightly below average in pretty much everything, but slightly above average in GPA. And cluster 4 is my slightly below average in everything and slightly below in GPA. I mean, I don't see much of a difference there. When I look at between the clusters, I'm like, there's not much. Just look at slightly below, slightly below, slightly below, slightly above, slightly below, slightly below, slightly below, and these border on decently below, but slightly below. This is the only difference between the clusters. I would not define that as enough of a key defining difference. So once you think that 5 does not have enough, because that's what we did here, 5 really didn't have enough key defining differences between the clusters, what are we going to do now? So 5 was like, I don't know about that. What are we going to do? This has been a good example problem kind of walking through. 5, I don't know about that. I don't know about that 5. Take it away. Take that away. No. We're not going to do that. And I think I mentioned this earlier, or at least went through my head. But Grayson, Mega 6. Here, this is for you, Grayson. So there you go. There's our clustering scheme. We're gonna go for 9. Yeah, this is. All right, let's clear some output here. All right, let's make our output here. I would go with the 4 clustering scheme. I think there's reason enough to say that there's differentiation between the clusters. And the 4 clustering scheme seems like a reasonable way to separate the clusters and to talk about the differences among the clusters. A lot of times, as stated, we look for z-scores that are extreme. Once again, we use z-scores to keep every variable on an equal playing field. We have the curse of dimensionality, which talks about that if we include way too many variables in this whole idea, everyone's going to kind of create their own separation. And we're going to see that the most similar is kind of the same distance as the most dissimilar items. So you really get these interesting things when you work with clustering that, once again, we're doing an unsupervised learning, meaning that there is no answer. I can't be like, that's the right answer. Also, we're using a set seed, because if I don't throw in this set seed right here, we'll get different answers. Let's just run it again. And if you notice, we get different answers. It might be different what it finds. Let me run it again. I want to see different answers. It moved the clusters by what they were called. It's moving around where they're at, but it doesn't have to converge. If I really want to get different answers, I'll take this iteration max way down, which is a horrible idea, at least putting it that low. Oh, good, 49 warnings. Warnings are good when you want to do something incorrectly. So what iteration max does, the way the k-means algorithm works, is we assign the cluster points first. How? How do we assign the cluster centers first? How do we assign the cluster centers first? It's one word, goes back to step 1. We're just gonna pick cluster centers at random, just boop, boop. And then what we do is we assign everyone to their cluster centers. Then we find the center of where everyone's assigned and we reassign them. Then we find those centers and we reassign. Then we find those centers and we reassign. Then those centers and we, wait, the answer just turned out to be the same. And these are the iterations I'm going through. So as I go through these iterations right here, I'm gonna go till I hit what? I'm gonna go till I hit convergence. It converges to an answer. It converges to an answer. Oh, no worries, no worries. It converges to an answer. That's convergence. It converges on the answer. It's saying this is the iteration max. It's gonna either converge or it's gonna go through the maximum amount of iterations. No, Maddie, you're fine. 100 points for making me laugh, Maddie. I appreciate it. So we'd probably look at it and say conversion. It's good right there. So what we have right here is going to keep going and keep going and keep going until finally it doesn't change the answer. That's convergence. So, but then you say to me, Brian, what the heck is that whole end start thing right there? Well, here's the thing. When you run the algorithm, pick your random starting points are going to control where your answer's at. So since your answer is controlled by the random starting points, how about we restart it and pick new random starting points? So the way we figure out kind of the lowest within cluster sums of squares based on where we assign the cluster centers would be based on going through the algorithm, restarting it, picking the cluster points at center, going till can we get convergence, okay, convergence, wait, restart the algorithm, go until you get convergence. Now the cluster centers are this time. When we restart, we go until we get convergence. Now we restart, we go until we get convergence. And that kind of deals with the whole idea of kind of a local max or local min. Don't really get into that, it's kind of optimization stuff, but within cluster sums of squares, that you could find an answer that isn't the best answer. And of course, this is telling me you did a horrible thing right here. Why would you use iteration max 2? I wonder if it'll let me get away with iteration max 10. That's probably high enough. It did. And if you notice, these answers are vastly different because, are they vastly different? They might be. Maybe they're not that different. Maybe this was a really easy one to k-means, but that's got it. Keep asking those questions. Keep going. What questions do you guys have? What do you want to cover? What do you want to talk about? Linkage, yes, the whole single linkage, yes, love some linkage. So let's talk about linkage, and we should have that here. I like the matrices. I misspelled linkage. 1B, let's go back here. We'll do 1B after this. I know it's in the chat. We should see. Let me pull it up in the notes then. Do we not have? Okay. Let me go back. I like doing it. Okay. Previous. Okay. No, I don't want to. That's the dendrogram right there. Oh, I think, is this how Petrie created it? Ooh. Wow, that's a lot right there. Okay, maybe I'll just display it. Oh, this is the whole thing that created it. It is pretty cool to look at all that right there. Let's hop back into the notes and steal it from the notes. Okay. Okay, so 2 seconds here. We talked about linkage sum this morning, and here's the biggest thing that I think confuses people on linkage. Whenever it comes to linkage, no matter how you figure out how you're linking things, whether it be single, whether it be complete, whether it be average, whether you use other methods like wards or anything like that, whatever method you're using for linkage, the biggest thing when it comes to linkage is we always link on the smallest. We always link on the smallest by our calculations. So let's go to the distance matrices we're using right here. So I do think some linkage questions are fair game. Let me command find in here single. It is not. It is saying there is way too much in here. Single linkage, found it. Okay. Can you guys, whoa. Okay. So we got Ward's method right here, which was on your homework, which Ward methods looks at the within cluster sums of squares of the merge, looking at the difference of the 2 previous ones. So we're trying to basically merge things together that when we merge them, their centers now have these smallest within cluster sums of squares. Word's an interesting one. Wouldn't have you really calculate that by hand because you'd have to calculate the within cluster sums of squares. Average is also something you can do, but that'd be much harder to calculate. So when we look at this right here, we can see this. And let's talk about my way of talking about it right here. Let me bring back up the chat, and then we will do the question here. I know it's been 1B has been a big one. So with this right here, the way I talk about this all the time is think about you've got a lifeboat right here, and they're kind of passing by. The shortest distance people can reach out and grab hands between their clusters is the single linkage. But this one is like throwing a rope between the two furthest away individuals. That's the way I think about single and complete in my head, is when you have two of the closest points. So is anybody in, like, I thought I saw one person in the library. So if you are in the library right now, I'll show you how to calculate some stuff here in a second. We'll do the distance matrix right here in a moment. But if you are in the library right now, what would define, if you were your own cluster, what would define the single linkage? The single linkage between you and someone else in the library would be the what distance? I know it's late, it's so late. I'm asking you guys to answer questions, but what would be the single linkage if you are your own cluster? And you can think of maybe the single linkage, if you are a cluster and other people are clusters, the single linkage would be you to the nearest person. But the interesting thing is, and that would be your single linkage with that cluster. But if everybody's by themselves, and we'll see that here with the distance matrix calculator right here. Okay, cool, zoom out a little bit. So at this point, it does not matter one bit if we are doing single or complete. This information on the screen would not change, and we would not change our decision if we were doing single or complete. Because think, 1 is by itself, 2 is by itself. I know we're linking it at this moment, but ignore that they're being linked here. 1 is by itself, 2 is by itself, 3 is by itself, 4 is by itself, 5 is by itself, 6 is by itself. They're all by themselves. So the way we calculate 1's distance from 2 is the closest thing in cluster 1, which is just itself, to cluster 2. And well, that's their single linkage. The complete linkage would be the furthest thing in cluster 1 from cluster 2. And wait, cluster 1 and cluster 2 are just single observations. So the distance between cluster 1 and cluster 2 based on single, average, and complete, but we won't do average on the test, at least I don't think so. The distances calculated right here would all be the same because it's the same distance. So there's really not gonna be much of a difference going on right there. And wards would put the cluster center in, and then we'd do the sums of squares. Unless we do a theoretical one, which was on your homework. I don't see you doing a distance matrices with those. So when you look at this right here, which clusters would merge based on single linkage? Hint, answer on the screen. But this is where I'm gonna trick people, and watch out. And this is where I don't want you to get tricked. 1 and 2. But if we change the question to complete linkage, which will merge if we change the question to complete linkage? Which will merge? Which will merge if we change it to complete linkage? And then I'll say something that will hopefully clarify it to everybody. Which will merge if we change it to complete linkage? Which, oh no, I've tricked you. I've tricked you. 1 and 2. It's still 1 and 2. And here's the reason. So, and here's the great thing. If you get something wrong on the practice, you remember, you're like, wait a minute, we would still start the same. Because when we merge these, we merge on the what-is distance. We merge on the what-is distance. When we merge the clusters, we merge on the what is the smallest difference. But when we say single complete, wards or average, the way we calculate the distance matrix changes. So the way that distance matrix is calculated in the next step will change. So go ahead and try to do this on your sheet of paper, and I'm gonna copy this and I'm gonna write it down. But I want everyone to try to do this for a second here. And I don't know, people be like, why'd you do like a test question? I'm like, I don't know, I just came up with it. So I want you to try to do this. I want you to try to write down the complete, I want you to do the complete linkage right here and write it down on your sheet of paper. So the first step is gonna be the same. We'll hop down here to the next one. And I don't think we actually view the map. Oh, here we go. Well, let me ask you this. With these calculations on this screen, this is a trick question again, watch out. Which two clusters would merge based on single linkage. I'm just doing repetition on you guys now, so get ready for it. And then we'll recalculate this distance matrix. See, this one's an easier one to calculate. 3, 5, and 4. Let me double check. No. 6 and 4. 6 and 4 are going to merge because the distance between 6 and 4 is this. Now, I'm going to grab this right here. Can I copy this into R? It's not going to let me copy that. Nice and neat like that, is it? What? Oh, it's horribly. So it's not going to work with that right there. We could go down here, Microsoft Word. Let's see, Microsoft Word. 2 seconds here, everybody. Get Word opened up. Chat blocked it. What did chat block? I'm so confused. When we merge right here, we're going to merge on 4 and 6. Oh, chat. Oh, okay, yeah. So we're going to merge on 4 and 6. And 4 and 6 will merge together, and then we'll take the shortest distance 4 is from 6. So when 4 and 6 merge together, what will 4 6's distance be from 3 5? What will 4 6's difference be from 3 and 5? So don't go to the next slide or anything. What will 4 6's difference be from 3 and 5? If we're doing single linkage, I should say that. If it's single linkage, what will 4 6's distance be from 3 and 5? Single linkage. If it's single linkage, what will 4 6's difference be from 3 and 5? Distance, I should say. What is the distance to the single linkage from the 4 6? You are correct. And great job, Lou, right there. It is this number right here, because if you notice, 4 is that far away, 6 is that far away. So when you go to the next slide right here, you will see, and this is just doing more decimal place accurate. It's just apparently is reported 2 decimals now, because we're into some really kind of close decisions. So 4 6 is that right there. It's just a more accurate decimal representation of what we see, that 4 6 has a difference from 3 5. And is that, let me just double check. 4 6 has a difference from 3 5 of that right there, and 3 5's distance from 1 2. Yeah, I see 3 5's distance from 1 2 is that, and that's 2.01. And this is 1.97 just rounded. Sorry, the decimals changed. It went to 2 decimal place accurate because, and you wonder why, it's because this is going to be this, and this is also going to be 2.0. So if we're actually going to decide which ones to merge next, we would see that. You know what's really interesting? If you go down here to the dendrogram of it, what you'll notice right here is that we see that these two merge right about here, and that's where you had that 1.97, and these two merge here at 2. So when we go back and take a look, if you notice the last ones merge at 2.01, and the ones before that merge at 1.97. So 1.97 is the distance from 4 6 to 3 5. And does everyone see the closest points? This is single linkage right now, is 1.97. Once you merge those, the closest distance, because this is single linkage, is going to be 1.25 right there. But if this was complete linkage, what do you think the distance calculation might be between these two clusters with complete linkage? What would probably be the two numbers we'd use to calculate the distance between the clusters? We'd use the distance between what and what? Which two numbers? Yes, 1 and 6 or 2 and 6. It's hard to tell, but one of those two, 2 and 6 or 1 and 6, because they're whichever two of the two farthest points. It's very hard to tell which one is, but one of those two combinations, and then we would just look at the distances between those. Which actually, why don't we just go cheat and look at that? It would actually be, to know the answer, 1 and 6 have a difference of 6.0, and 2 and 6 have a difference. So Sullivan right there, 50 points. I'm throwing some points tonight. So it would actually be 1 and 6 are the two furthest points. So kind of close, but that would be, we would use that calculation to see at what point they merge. That number right there would then show up in the dendrogram over here as the height at the point at which they merge. This height in the dendrogram is the value at which they merge, the distances between the clusters. So remember, this was 1.97, this was 2.01, which is why it's just barely above there, barely above. And so you'll see that the first one's merged at 1 and 2 merged at a distance between them. The shortest distance between 1 and 2 was about 1.4. The next things to merge was 3 and 5, which had the shortest distance between them of 1.74 or so. The next things to merge was 4 and 6, which had a short distance about 1.85. Then 3, 5 merged with 4, 6 at a height about 1.97. Then everything merged together. And when you look at these dendrograms right here, we can use the cut tree function, pretty cool, that we can cut them off. And let me zoom out just a little bit here. And we really want these nice kind of like clear, I call them legs. And this one, this is too nice. You don't get this. Oh, it's so beautiful. Because I think most people would agree that cluster, 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 cluster. And when you do that, you get this right here. We'll look at the elbow plot in a second. I'll pull up some elbow plot. This is more what you usually see. This is kind of more real data. You know, you like to do the kind of like quintessential example of like, oh, if everything looks like this in the world, that's what you would do. But what we have right here is the way real data looks. And we do have some nice, I would either go for a clustering scheme of how many clusters here. What are the 2 amounts of clusters you might use here? I don't know if teacher will put this on the test, but I always think this is, if you know how to look at a dendrogram, at least is the way I used to look at them. I'd probably start by investigating what right here? Clusters of how many or how many. This is why I call it the legs. You really want to see almost like it's got like legs right here, like there's a leg, or it's 4-legged. It's like how many legs does it have? That's what I call it. I just make up my own terms sometimes. But you see you can get a clear cut in here. You got a lot of area to cut where you don't hit. It's nearly impossible to get that 3 cut right there. You'd have to cut across here and somehow 3 clusters does not seem to be the way to go. You're really seeing that these kind of merge into the 2. So that's why when you look at this data, the way it looks, you either see kind of 2. I don't know. I'd love to see these points colored in the way it looks with 4, but maybe, I mean, there's either really 2 clusters or somehow kind of a 4 cluster scheme. And doing the 4 clusters does seem to be a viable option. I'd go back and I'd start assigning those clusters. I'd look at it. But once again, there is no answer because it's unsupervised learning. It's just like, well, I don't know. Let's see how this goes. Let's try some stuff out. Let's see if we get some money with it. Let's test it out. Here's the delta data frame right here. Hard to see, but this is everybody with all by themselves. This is a agglomerative method. The agglomerative method means that we're doing from the bottom up, where the k-means algorithm is going to be divisive because we're basically adding another center and we're dividing everyone up. So divisive means in my mind. So this is agglomerative where everyone starts out by themselves and then we start putting people with other people or things or whatever we're doing to cluster. And so those are kind of our 2 methods right there. We should see some good elbow plot. Let's go look at an elbow plot here. So this is kind of similar here where we're looking at the number of clusters and the cut height, a little bit of change. And let's go back and look at elbow plot with the k-means. This is for k-means, but I was just thinking we didn't cover it. So we hop back and talk about this briefly. If you remember, one of your assignments asked you for kind of the ideal within cluster sums of squares. So when you look at this right here, this would be, wow, this is amazing. What do you want your within cluster sums of squares to be? What would you love that within cluster sums of squares to be? We would love for that within cluster sums of squares to be. Well, that's how many clusters you want to use here. And I think this actually goes to the, if you can tell, it goes to these plots right here. I was like, I think it's going to be where it's pretty clear. So as we add, and this is hopping back to k-means a little bit here to hop away from dendrograms and distance matrices for a half second. When you look at this right here, the within cluster sums of squares reduces every time we add in a new cluster center. So the addition of a new cluster center allows things to be closer to their cluster centers. Does that make sense? Like, even if we add in another cluster center here and another cluster center here, things are going to be closer to those. So every time we add in a cluster center, it's always going to help. But you got to think about it. It's like, after what point, which I think, Ben, you've basically answered, after what point is it like, it's not really helping anymore? I mean, it is, but it's like this. Imagine this is the plane trip that gets you to New York. And then you're outside your friend's apartment in New York. And he walks you in and he's like, oh, I brought you to New York. And you're like, no, you didn't bring me here. And he's like, I walked you from the doorstep to the apartment. You're like, well, he's like, it counts. You're like, no, yes, it helped. But all the work was done by the first 4 clusters. And that's what you see in this graphic right here. So you see a cluster here, a cluster here, a cluster here, a cluster here. And when you look at the within cluster sums of squares of those 4 clusters, it's doing all the work. Yes, if you add more clusters, it's gonna help. I mean, because yeah, things can be closer to cluster centers if we make more cluster centers. But at this point, it's not really returning anything. I guess theoretically, if points are stacked on top of each other, you could achieve 0, and then you would your clustering scheme would not get any better. But the lowest within cluster sums of squares you can achieve is 0. And in this theoretical example here, which theoretical examples are really good to show kind of how everything works, we basically achieve 0. Let's hop back to question 1B because it is 8:30. I'll cover any other topics you guys want. 1B says, how many brands have at least 80 listeners? How many brands have a support of it is less than, if we consider only rules. So if you think about this using your a priori learning method, so this is to Jack and everyone else and Michael. So what we have right here is this is a parameter. I'm trying to copy it. It won't let me. Oh, there we go. The 80 over 182 is what we could do as a parameter right there. So we want bands with at least that many listeners. We want at least that many. So with this in mind right here, we can kind of limit what we're looking at. And then what does the rest of the question say? Well, once you get this right here, and Dr. Petrie's hint is very accurate. I'm not trying to give away the answer, but he's very accurate to say it's only a little. Maybe 1, 2, 3, 4, 5, somewhere in that range. Only a little. Like, what does a little mean? It doesn't mean a lot. Like, if your friend gave you this amount of money, you'd be like, and they basically gave me 150. Basically. They didn't, but a little. So you should get a number a little less than 150. If we consider only rules of length 3, A, B, C, with these bands, use the choose function to determine how many possible rules exist. So if you know the answer, I don't want you to tell me how many bands there are. I want you to give me a wrong answer in that range. I'm going to pick a wrong answer. So I'm kind of narrowing down your answers here. So give me a wrong answer in that range. Let me bring back up the chat here. So give me a wrong answer in the range. So I'm going to eliminate another answer for you, so you get a little help on the assignment here. So give me a wrong answer for how many bands meet this criteria. And this goes back to something I mentioned earlier tonight. What is a wrong answer? No, wait, no. Remember, it's a little less than 150. A little less than 150. We should find a little less than 150. A little less than 150 bands. I'll probably wait till there's 2 answers. That way someone says the right one. But even if there's 2 answers, doesn't mean one of them's right. A little less than 150. Why don't we just use 150? Because that's not the answer. So, yeah, and that's what I was getting to right here, Michael. So I just want someone to, okay. So here's what choose does again. So with choose, what it does is it's kind of the permutations. I think I'm using permutations correctly. It finds out, and probably we could do the question mark on it, but I'm 99% sure permutation is the accurate word for it. If I said for you, imagine this, Michael, I said to you, I've got 150 bands for you to pick from to put on your playlist. I want you to pick 150 of them. How many ways could you choose 150 bands if I have 150 bands to pick from? Yep. There we go. If I said you can pick 1 band, how many ways can you pick 1 band? If I say I've got 150 bands for you to pick from, just pick 1 of them. 150. How about if I said you don't get to pick any bands? You pick no bands here. I don't want you to pick any of my bands. Careful. How many ways can you pick no bands? There you go. Yeah, and that's the key is like always think about what your function's doing, like use some, and great job, Michael, 50 points, just throw those points out to you guys. But always think about what the function is doing and think about like examples like, okay, wait, is it doing this? Is it doing this? Okay, it's saying if I have 150 bands and I can pick 0 of them, how many ways can I do that? So choose from 150 things, 0 things, and how many ways can you do that? So if I were to say, okay, it gets complicated now. Has anyone ever seen the classic, what is it called? The golden triangle where you have the numbers where it's like you can, if you look at this, like how many ways can you pick one thing 1 way, there's that way, or how many ways can you pick 1 thing 0 ways, there's 1. But it gets complicated because you say, how many ways can you pick 2 things and pick 0? You have 2 things and pick 0, that'd be 1. And 2 things pick 1, that would be 2. And then 2 things pick 2. But now we start to get into the harder ones. 3 things pick 3. Well, you can pick 1 thing from 3 ways, and you can pick two things from three ways because you basically leave one out. And this is where your brain really gets taxed if you start to think about things like this. You have four things and you need to pick two. That means you would pick this one, one of those, that's three. You'd pick this one right here, and then one of these remaining two. So that's 3, 2, 1. That should be 6. So it's the Pythagoras triangle, golden triangle, something like that's the name of it. So it's the ways of combinations we can have stuff. So hopefully I'm not using combinations or permutations mathematically inaccurate, but it's just saying you have four things. How many ways can you pick two? So when you think about, yes, the cheat sheet needs to be handwritten cheat sheet. Handwritten cheat sheet. I don't know why I'm doing accents right now. I don't even know what the accent is. So this is saying if I have 150 things to pick from and I pick two, how many ways could I do that? And think about this, when we talk about rules are basically like you can have four things picked for a rule. And so with four things being picked for a rule, you would talk about, like how many combinations of rules you can get with four things being picked for a rule. It's kind of the important thing right here. How many different ways can you pick four things and kind of create rules from it? So pretty crazy amounts of stuff right here. The ways in which you can pick four things and create rules from them. So lots and lots and lots and lots and lots and lots of ways to pick four things and then create all the rules from them. So that is definitely it. That is correct, Cooper. No typed cheat sheet. I did confirm that with Dr. Petrie. So be writing down your, oh no. Did confirm that. I might try to do that, Maddie. I might try to do that. I'll have to write up a Kahoot for this. Oh, you guys that's awesome. Was this helpful tonight? What do you guys feel? So here's a good thing. Remember, all the lectures are recorded. I'm probably going to be a little. Oh, thank you guys for the very helpful. I'm glad to hear that. I'm probably going to be a little burnt out tomorrow. Because I'm going to be teaching tomorrow, and I've got reviews tomorrow night until 7 or 8. Give me topics you guys want me to talk about tomorrow, because do remember, you're welcome. So the review I did this morning was mainly more of this, but tell me topics you want me to talk about tomorrow. You could email them or just say a few things you guys want me to talk about tomorrow, and we'll focus tomorrow's class on that. I'm trying to think what we missed. Maybe I should do some for loops and while loops tomorrow, like reading that code. Maybe I'll ask Petrie if he saw some of this. I mean, he saw some summary of what's going to be on. I wish I could, but I can't. I think a copy. There is no amount of money. I love my job too much. I don't even have a copy of the exam, so I can't. But Petrie and I have talked a good bit about what'll be on there. He gave me a lot of good tips for you guys. And I feel pretty confident that with what I've told you, you should have a very good inclination to about, I would say at least around 60% of the exam should be pretty revealed to a certain extent. That, we covered some stuff tonight where it's like, I bet there's going to be a question a lot like that on the exam. And I hope, because I want these reviews to be worth your time. Well, Petrie was in here and he wasn't saying, Brian, talk about this. And he did send me some suggestions and I read them off verbatim. I'll leave the review tonight, especially. Let me read those office hours tomorrow. Office hours tomorrow are from 2 to 5. 2 to 5 are office hours. Tips for tonight. These are the tips coming straight from Petrie. And he does have the review stuff. Tomorrow to start class, I'll go to his review slides, and we'll look at those in class. And then I'll maybe do some for loops and while loops, or maybe Petrie will give me more advice on what to do. And so if you're not in my section, you can watch that, or you can come to class tomorrow, which is 2:40 to 1:55. Be comfortable interpreting MD pattern. He's putting a lot of questions, not a lot, but he's going to put questions on MD pattern. So be comfortable interpreting MD pattern. Don't skim the problem descriptions. There's quite a few sets where like you better know what the problem's talking about. You better read the descriptions and know what it's talking about there. So make sure you can do the in context, especially for clustering and validation, because that's key to actually doing clustering and validation is like, you got to know your data. Being a subject matter expert is very important. I always say my brother's better at pharmacy statistics than I am because he's a pharmacist. I might be kind of, I don't know. I give him a run for his money, but I'm better at stats. He's better at the pharmacy. Number 3, you'll want to be really good at interpreting cluster centers and coming up with descriptions of what individuals in each cluster look like. So you kind of want to talk about the clusters themselves, like come up with some sort of idea, description, or kind of general theme for the cluster. Then you want to differentiate the clusters from the other clusters. Be like, this cluster is this. How do they differentiate? Look at the z-scores, look at the means with the aggregate and the medians. We did a lot of that tonight. You'll want to know how to determine if adding a cluster is worth it, which is going to boil down to a pretty deep understanding of the business problem the clustering is trying to address. Man, I'm excited to see this question. I'm like, what is he going to do? Like, what are they trying to, so like, I feel like I'm gonna, he's like, Brian, you gave it away. Like, just think about what he said earlier. What are they trying to analyze? What are they trying to understand? Like, what is their goal? So when people say like, why are you making clusters? It's like, yeah, why are we making clusters? What do we want from this? And there's no objective, reason to make the clusters. There's no way to gauge it unless we can say like, here's kind of what we had in mind. Like we want to maybe identify students who maybe like have low GPAs or something. Like maybe that's what I want to identify. So then if we're seeing people cluster based on GPA and then we're seeing something else, I feel like people are like, you totally gave away the question. I don't think he's using GPA and all stuff like that. I think he and I are at least kind of different mind tracks. But it really boils down to what do they want to understand, what's going on. If this is unsupervised learning, how do you guys agree? Maddie, I'm throwing the 100 right there. It's a big thing is like unsupervised learning does not mean we can't objectively look at it. You just set a criteria that is outside of, like you can't get an R-squared, you can't get a misclassification rate, because when we do later things, we'll be able to look at the misclassification rate. So this is kind of a look into the future with like support vector machine or for instance, neural nets, all that other great stuff we're going to do later on. You can look at, or we've just got vanilla regression, we got logistic regression, we got lasso, elastic net, we got ridge. See, now my brain just went turned on. So with all those things right there, usually we have some objective measure to look at it, like R-squared, percent of variation explained by our model. We have R-squared holdout to see how it does on new data. We have misclassification rate if it's categorical to see how it's working on both the current data, training data, or new data. All those things are about to come up later in the semester, which I find cool. We're gonna use the carrot package, one of my favorites. But at this point, when we look at how our things doing, we have to be like, well, what's our goal and how can we kind of talk about our goal? Because there's no real answer to this. There's no like, if we're the University of Tennessee and we're trying to identify students who might fail out and we're making clusters of students who might fail out, well, then we need to kind of, probably have clusters that somehow separate them by GPA, but then we need other identifying things within those clusters to kind of identify some groups. And then we need to make some action we're going to take. And then we need to maybe market it out, like test market it to see how it works. And then like if it's a costly plan, like we're saying, oh, this is going to cost this many hours and money. So I like the business aspect of this because it's like, well, how do we implement this? How do we do all this? And that's the business of business analytics. The numbers is just our best understanding of what's going on. That basically has it. How you guys doing? What are you thinking? Is anybody left? It was so crazy. Like, no, I think there's still people in here, but what would you suggest studying and churning through the practice tests? What's the best way to study for the exam? I really think homeworks are a great way. I think homeworks and activities. Here's the biggest thing. I think I've given some great advice tonight. And I hope that someone gets to a test question, they're like, oh, I got this because of Brian. That'd make me feel special. If the whole test was given away, and I'd be like, oops. But I think we definitely touched upon a lot of things that will help you on the test. Petrie's writing the test. And with that, he wrote the notes, he wrote the activities, he wrote the homeworks. The test is going to focus more on probably interpreting output and being able to understand conceptually what is happening. So being able to understand the output and what it means is the key. And you notice we focused on that a lot tonight because I was making output and reading the output, especially with like the k-means algorithm. I was like, oh, let's look at what these clusters mean right here. Okay, let's increase the clusters. So I would maybe even do what I did, see if you can recreate the clusters and kind of walk through what I'm doing with the creation of the clusters. A lot of it's just augmenting existing code if you already have a lot of the code. I hope that helps out. So I would focus in on the practice problems. There's a lot of practice problems. and I would make sure you can interpret. Try to interpret things outside of what we ask you to interpret, and the keys should be posted for pretty much everything. Other questions? If not, we'll finish up. And I hope, and I'll try to do some new stuff tomorrow. A lot of what we did tonight, not all, was covered this morning, but is the review going to be posted? Yes, I'm going to post this on the 320 channel. So I'm going to post this on 320. It'll be posted later. Night, Ben. I'm going to post this later tonight. Signing off. Thanks, Grayson. You're welcome, guys. Thank you, Maddie. Thank you, everybody. So this is it. Great job, you guys. I will post this. And so I'll probably send an announcement to everybody, say, hey, it is posted, 320 channel. That's got it this time. Last time I hit end meeting, and then it didn't do it because I have to go back to my screen. I have to stop screen sharing, and then we're going to go to end meeting for all. So good night, everyone. Talk to you later.